Alrighty, reaction quotient and Le Chat's principle. So 7.9 was about doing things qualitatively, meaning I'm increasing an amount. I could just talk about shifting left and right or, increasing forward and reverse rate. But that's not quite as accurate versus using Q. Plus, a system might be stressed in several ways. I might increase every single thing, and then we have to see how that affects the system, because if I increase it by certain amounts, you won't know exactly how it is unless you calculate Q. So Q is quantitative because I can take KQ, it's the same thing for Q, except, it is any situation, and it is way more accurate compared to Le Chat. Again, Le Chat is handy for when it's like easy stuff, but if it's more complicated, then Q is better. So again, Q is reaction quotient in case you forgot, and it is the reaction at any time, so the amount of product versus reactant at any time. And so whatever your Q value is, you can figure out what direction the reaction is going to go in order to go back to equilibrium. Because remember, K is a constant for equilibrium, and so Q is at any point. And so if Q is different from K, then it's going to shift back to equilibrium. So, example. Here is that. Cool. And so here's a quick little mini your turn. So here are the initial concentrations of everybody. Go ahead and calculate Q real quick. Did you do it? Okay, so if you noticed, O2 is 0. So if I calculated Q, it would be 0 times this number, and then divided by this number. So 0 divided by anything is just 0. So my Q value is currently 0. That's the initial concentrations, because that's what it says here. Okay? And so, as a reminder, for equilibrium, you need everything in some amount. So you need a little bit of everybody in some kind of capacity. So there is nothing that can have a concentration that is 0. So this O2, for example, was 0. That's the initial concentration. But you can technically have something, like it has to eventually compensate for that, because K has a value. You can't have something at 0. That doesn't make sense. You can't multiply by 0. You can't divide by 0 in order to get a K value. So that's just, quick little note thingy. Now, since we have something at 0, how will this reaction proceed to go back to equilibrium? Because equilibrium is K right here. And so you could think about it in terms of Le Chat, like I said, but this is just an example we're doing to do Q values, right? And so I think about ratios. So I think about the top versus the bottom. And so Q is less than K currently, because Q is 0, K is 4 times 10 to the negative 16. And so that means that I need to increase the products, because if the value is smaller for Q, that means my numerator, the top part of the ratio, is not as big. And so that's why I have to go towards the product side. So I'm going to increase that forward rate. And so what's going to happen to CO here to reach equilibrium based off of this whole thing? CO is going to increase, or the concentration of CO is going to increase, because I'm increasing the forward rate in order to make both things, because I can't just make one of them in order to go forward. I have to make both simultaneously. So, in general, if your Q is less than K, your reaction is going to favor formation of P, as in products, until your equilibrium is established. And so then once you're at equilibrium, then you're going to have the same forward and reverse rate. So you're going to increase that forward rate in order to make product. And there we go. Cool. So, same thing as earlier. Quickie mini your turn. Go ahead and calculate this real quick. So I didn't actually calculate this. I forgot to. But Whatever that Q value is, I know it's greater than K because I have it in my notes. But whatever that Q value is, it should be greater than K, right? And so because the Q is greater than K, that means I need more of the denominator. And as a reminder, the denominator is reactants because K is written as products divided by reactants. And so since my Q value is bigger than K, that means I need to make more denominator. I need more reactants. So I'm going to increase the reverse rate to reach equilibrium. Then what's going to happen to CO? Well, since I'm increasing the reverse rate, so I'm going backwards, that means the concentration of CO is going to decrease. Cool. So, in general, if your Q value is greater than K, then you're going to favor making reactants, so you're going to increase the reverse rate in order to eventually establish equilibrium. Now again, these examples are really easy because you're just plugging in the values for Q and stuff, and so just be mindful of that when using this stuff. Okay, so summary. Q is better than Le Chat because it is based off of actual calculations. Yeah. As a reminder, to get equilibrium, if Q is less than K, you have too many reactants, so you're going to increase the forward rate in order to form more product, because product's in the numerator side, as you can see here. And so if Q is equal to K, they're already at equilibrium. Because remember, Q can be at any point. If Q is at equilibrium, then obviously the forward rate and reverse rate is going to be the same, because that's what equilibrium is. And so if Q is greater than K, you have too many products. So again, because this is bigger, the numerator is bigger. And so then the reaction is going to go reverse because you're going to increase the reverse rate. And then you're going to form more reactant until you reach equilibrium. Cool. So here's another diagram of just like earlier, just explaining the same thing. So this chart is similar to 7.9, except now we have Q. We can write down Q and actually do all the things for it. So we're going to fill out this chart real quick. Okay, so we're going to talk about each of these. And as I wrote here, it says include the heat term. As a reminder, the heat term is not part of Q. We just use it so it's easy to, notice, right? And so we're going to go ahead and start doing it. So Q. I'm going to write the Q for this. So Q equals A to B, because it's products over reactants. And so it's exothermic because negative means exothermic. So exothermic is a product. So I'm going to put heat here. Cool. And so if I'm increasing the temperature, I'm increasing the product side. And so when I increase the numerator, that means my value for Q is going to be more than K. So the reaction will proceed toward the reactants because I have too much product, I have too much heat. And so I'm going to increase the reverse rate. Okay, so my Q is the same as the above, so I'm going to be lazy and do that. This is just the same as this. And then I'm dropping temperature. So the heat here is decreasing. And so since that's decreasing, my numerator is smaller compared to what it was originally. So that means my Q is going to be less than K. And so the reaction will proceed toward the products. It's going to increase that forward. Alrighty. So Q here. So Q equals A to B, and then A to B. Cool. And so this one doesn't have heat involved. It just says add R. Oh, this both says add R. Did I mean to do that? Let me think. Okay, I'll go back to this. I know why. Okay, so for this one, we're adding reactant. So reactant is the bottom number. So I'm increasing that bottom number. When I increase something on the bottom, remember you're dividing by that number. So what happens to the Q value? I'm dividing by a bigger number, so that means the overall answer is going to be less than K. And so we're going to go towards making product. And, you know, it's the same phrase. Reaction will proceed toward, you know, just reactant versus product. Okay, so for number 4, so adding reactant. Now, this one is interesting because it's all gases. Notice that this was AQ. These are gases. And so you have to consider what's happening in the situation. So, for example, when you think about gases in terms of concentration, remember that concentration is N divided by V, N being moles and V is volume. And so when you're adding reactant, it totally depends on what's happening to the volume as well, because the ratio of moles versus volume depends. So honestly, it depends. Like, is the volume constant? Is the volume not constant? And so the problem has to tell you if that volume is constant or not. Because if the volume is constant, that means adding R is increasing the N value, but not the volume overall. And so you have to look at, you still look at Q, but you need to think about it in terms of N divided by V and not just a number. So you're not just inputting a molarity. You actually have to think about, again, is the volume constant or not? Because that changes the molarity of everybody if that volume is indeed changing when adding the value here. And so you actually would need more information in order to do 4 in general. Okay. Number 5. So dilution. So remember dilution means adding water into the situation. Because these are all AQ, so they're all dissolved in water. I'm going to go ahead and write the Q for this. Products over reactants. So remember, water is a dilution, and honestly, it depends on the reaction. And so, if I'm diluting this, I'm changing the V part here. And so I'm going to show my vague work on this with an example to show you what I mean. Okay. Let's say for this dilution, let's say I doubled the volume, okay? And so as a reminder, the molarity is N divided by V. So I'm going to use just N divided by V. I'm not going to distinguish which one is which, because I could if I wanted to with subscripts, but I'm lazy. And so the dilution, again, is I doubled the volume, right? So on the top, we have N divided by 2V, because I said I doubled the volume. And since this is all in the same, beaker or whatever this experiment's happening in, the volume's going to be the same for all of them, because they are literally together, right? And so then for the bottom, we have N divided by 2V, we have N divided by 2V. I'm going to keep all the V's. I'm just going to focus on the 2. So the 2 cancels out here and here, right? And so I have N divided by V divided by N divided by V. And then I have N divided by 2V. And so as a reminder, if you have a division in the denominator that is flipped up, I don't remember what that rule is called in math, to be honest. But it looks something like this. Okay, so again, I diluted this by a factor of 2. I doubled the volume. And so notice my Q value increased by 2 compared to whatever original K is, because original K is just N divided by V. If I double the volume here, then my Q is now double. So now it's 2Q, which is greater than K. And so, again, water is just diluting this. In this particular example, my Q is greater than K. So, again, be very careful. This is going towards a reactant because Q is greater than K. And so the dilutions, it depends on who's involved. So obviously for this particular example, I'm going towards reactant, but it could very well easily go towards product. Again, just do your work, do something like this in order to see if diluting is going to increase or, the forward or the reverse rate, because it just depends on how that volume is affecting the original equilibrium constant. Cool. Okay. And then for number 6, decrease in volume. So, you do the same thing with the N divided by V thing. So you can do it exactly how I did the dilution example. I'm not going to show that again. So I'm just going to say Q is greater than K. And so since Q is greater than K, we're going to go towards the reactant. Cool. And then I could do the same thing for increasing volume here. I could show my work similarly to this one. I'm not going to because it's, same situation. So the Q versus K, it's going to be Q less than K. And so since Q is less than K, we're going to go towards product. Cool. So for the, messing with volume, whether it is dilution, whether it is volume for gases, just keep in mind that concentration is N divided by V. And so since it's N divided by V, I can mess with the volume part and then see what happens to the value overall. Cool. Okay. Alrighty. Using Q to help you get the concentration of equilibrium for everybody. Okay. So, here's a problem. Got a K value, got some initial concentrations. We're going to get the equilibrium. So first, calculate Q real quick. Put your Q based off what is on top, what's on bottom, and then fill it in, and then calculate. Alrighty, ready? Here we go. Here it is, 1.8. And so 1.8 is Q. Again, K is 4, so Q is less than K. So which direction will this proceed? Again, if you get stuck, remember it's products over reactants, so think about the ratio. And so since Q is less than K, that means I need to increase the amount of product because I need to increase the numerator. So the reaction is going to go forward. All right. So since we know Q versus K, I could do a Rice table for this. And so this is why, this is the main reason why we're talking about Q versus K, because in order to know exactly what values we're going to get for E, I had to know if I'm going to increase the forward or reverse rate in order to do the C part of the Rice table. So first thing you should do is just fill out as much as you can. So the R, the I, if you can do the C and E, go for it. Again, I'll talk about how to fill this out based off what we just did with the Q being less than K in a second. So pause. Okay, ready? Here you go. So, like I said, we needed to increase the making of product. And so that's why the right side is positive X and the left side is negative. Because again, if I go back here, Q is less than K. And so we need to increase the forward rate, aka increase making more product. And so that's why the C part is positive on the product side and subtraction on the reactant side. Because again, we need to make product. We're comparing Q and K because math ratios. We love math ratios. Okay, so Whenever I have a rice table, I always like to check if the shortcut works. So 100 times K, is it less than the initial reactant concentration? And so 100 times K, so that's 400. 400 is way more than these, so the shortcut doesn't work. I can't make these just E equals 0.030, so I have to actually like math because the shortcut doesn't work. Solve for x using math. Okay, so let's math. Okay, so I'm showing all my work for those that don't get the math. You don't have to show every single math step. As long as the grader knows how you got x, you're good, just as I said here. So for those that are good at doing algebra in your head, you could skip some steps. You don't have to show every single algebra step, as long as it makes sense. Now, obviously, if you get hella lost in the sauce, show all your work. That way you don't make a mistake, because I definitely do easy algebra mistakes. You've seen. Frickin' adding numbers together and whatnot. So, show your work if you need to. So I'm inputting my E values into the K constant. And so here it is. And so these are squared. Since they're both squared, that means I can square root both sides because it's a perfect square. So that's what I did here. And so then I multiplied by the denominator, and then I distributed the 2, meaning I multiplied the 2 out here and here. That's where that value comes in. This is the right side still. And then I solved for x by adding 2x on both sides, subtracting this over there, and then dividing. And then I got my x. So I definitely did skip a couple steps here. But if you want to show every single step, go for it. So the original question was talking about what is the equilibrium concentrations of all these species, so make sure to plug in your x value and then actually answer the question. Remember that we're used to solving for x in math class and then you stop, but you have to read the questions like, do we actually solve the bloody thing? And so you gotta check. And so we have our concentrations of carbon monoxide and water, and so we plugged it in and we got our molarity here, and then I got my carbon dioxide and H2 and I plugged in my X and then I put it there. Cool. Oh, I didn't check sig figs. 2. Yeah, it's just 2. Okay, cool. So again, make sure you always check what the question's asking for in order to solve for your rice table. Okay, here's your turn. I gave you some hints. I shorthanded the question because I got lazy. So you're finding the concentration of everybody at equilibrium. So here's some hints. Ooh, it's quadratic. Ooh, how evil of me. Here's checking your x values. So I actually give you the x values for you to practice. So practice this first before you look at what I have. Okay, ready? Here's what I got. Bam, bam. Move this over here. Oh, what a tiny, cute little rice table. Cute. So, I have my K. I have some stuff. I multiplied this on this side. I made everything together. I used negative b plus or minus the square root of b squared minus 4ac. You know, the whole quadratic whatever. And so, now, remember the quadratic gives you 2x values. Which one makes sense? The second one does, because the first one gives a negative, as I said here. So if I look at NO2 and I plug in 0.8 here, I'm going to get a negative value. And there's no negative concentrations of anything. It either has 0 or it has an amount. You can't have a negative amount of something. That doesn't make sense. And so I use the correct x value, which is going to be this one. And so I plug those in, and then I answer my question. Bam! There you go. That is it for this section. Cool. Bye.